My name is Sasi Pillay. I'm the Chief Technology Officer for NASA. And I'm here today to tell you about information technology, the current aspect of the profession, and what it means to be an information technologist, and the amount of professional jobs that are available in this country, and then how you can go about preparing to be an information technologist. First, however, before we get into the specific aspects of information technology, I want you to watch a video that was put together by Corning Glass. This really paints the vision of the future. Some of the things that you see in there regarding mobile technologies, I'm sure you're already aware of it. How many in this audience have a mobile phone or a smartphone? I can see from the response there's a large majority of you already are familiar with that technology. Guess what's going to be happening in the future? There's going to be more and more of those mobile technologies. I think I read a report somewhere that said there are more mobile and smartphones in the world than toothbrushes. Can you imagine that? This is, so you can see how exciting that's going to be. So I think you should pay particular attention to this video, which specifically talks about how mobile technology and the whole concept of being able to work from anywhere is incorporated, and how easy it is in terms of the user interfaces. As you already know, many of the newer technologies are using touch and gesture technologies to control and manipulate what you want to do, as opposed to typing on a keyboard. And again, you'll see that in the video as well. hopefully you had a chance to watch the video and enjoyed it, and hopefully now you're already, before you get into the rest of my talk, has enrolled to be a future information technologist. Now, let me go back and be very specific what some of the specific areas in information technology. So first and foremost, let me talk about robotics. As you know, in terms of the Industrial Revolution, many of the folks who are working in the assembly line had to do lots of work that was kind of dangerous, whether you're working in a nuclear reactor or an assembly line or in a steel manufacturing capability or facility. You need to have something that will actually make sure that you're safe as an employee. Robotics actually can do that. And by the way, at NASA, we use robotics extensively. I'm sure you had the opportunity to watch the Curiosity robot be hovered and soft landed on the surface of Mars. So robots can be used extensively where human presence is it's not conducive. Mobile computing, I already mentioned quite a bit about that already, but as you can see, that's an area that is just blossoming. And I'm sure the video that you saw by Corning, The Future of Glass, already made sure that you understand where that technology is going. The next topical area is modeling and simulation. As you can see, at NASA, for example, we have large wind tunnels where we test models. And the way we test these models is to understand the characteristics of flight and lift for aeronautics. And this is how we design the next generation aircraft and space vehicles, because you want to fully understand the boundary layers regarding how air, when it flows over a model, separates and how that either enhances or inhibits propulsion. So these things can be done in a wind tunnel where we measure these things and actually conduct the experiment. But as you can see, to run a wind tunnel, it's quite expensive. It requires a tremendous amount of energy, and most often we do that only in the evenings when the rates for electricity is much lower than during the daytime. But one of the things we want to do as far as modeling and simulation is concerned is to be able to actually model the physical phenomena related to the physical model of an aircraft or a spacecraft. If you're able to do that in what we call cyberspace, which is basically using information technology, you should be able to then simulate very many of the same characteristics that you would see in a physical model. Now, if you can do all that and then actually predict some of the outcomes of our testing without actually testing, as you can see, it saves significant amount of money. And NASA had a program called Numerical Propulsion System Simulation in which we attempted to do that. And much of that code that we wrote for that particular environment has been incorporated by both Pratt & Whitney and General Electric in the design of their next generation engines. As you know, when you come up with a new engine, it has to go through a significant amount of flight test and safety analysis before it can be put into production. By using codes like the one that NASA developed, you can actually significantly increase the time to market from an idea or a design all the way to production. So these two companies have actually embraced and actually using the NASA developed code in their production systems for the next generation engines. So whole concept of my describing that is to be able to work in an environment in which you're combining scientific principles, but using those principles to essentially model and simulate how physical characteristics can be duplicated in cyberspace, and then derive results with it without actually having to go through the expensive and time-consuming process of testing. Now, closely coupled with this is what we call a concept of visualization. As you know, when you go into computing and you generate lots of data, that's for sure. But how can you sort through this data? A human being cannot really comprehend all these data. I mean, a simple example is, by looking at a table of numbers, it's hard to understand what the trend of that data is trying to tell you, unless you're able to graph it, a simple XY, a Cartesian coordinate-based graph. Now, once you graph it, you can see the trends quite easily by visualizing it. But you can also see the rate of change of that curve. These things are next to impossible to understand and comprehend if you're just simply looking at a table of numbers. So you can see when you're looking at multidimensional data, if you can actually visualize that in three-dimensional, and you're able to create an environment in which you can immerse yourself in the data, in which you can look around and turn around and see all the different aspects of the data, you can further and better comprehend what the physical phenomena is doing, far better than looking at a table of numbers. So visualization is a key concept in terms of being able to comprehend much of what we're talking about in scientific data and analysis. Once you couple visualization with what the previous topic that I talked about, which is modeling and simulation, you can see how significant of scientific breakthroughs that you can have as a result of combining some of these techniques. And the next one is called decision systems. And as you can see, it gets more and more progressively difficult to do this. But you can see it's built on the previous elements that I already talked about. Decision systems is a situation in which, and one of the programs that NASA has attempted is to be able to collect information from multiple sources. So just imagine you're a pilot flying an aircraft, but the weather has suddenly turned for the worse. You would like to make a decision whether we should land the plane or continue flying. In other words, we like to understand the risk profile of continuing to fly. Now, as a human being, there's only so much data you can comprehend and analyze and then make a decision. What we want are computer systems which will assist the human being to be able to make that decision rather quickly. So in that particular situation, what we need to do is to take the data of how the current engines are performing based on all the sensory data that we are collecting. We need to understand the history of that engine in terms of its maintenance history as to what type of service it has already provided and the life of the engine, etc., and so on and so forth, and how many times it had to be rebuilt. Then it has to be coupled with the prevailing weather conditions and the forecast and the weather patterns of the area that the aircraft is going to be approaching. So you can see by combining all these dimensions of or domains of knowledge, one has to make a decision based on safety of the aircraft and its passengers. It's impossible to analyze, even if you could, all that data quick enough to make an important decision. This is how a computer-assisted technologies can do that. Now, can you imagine taking all these domains of data and be able to visualize it so that the pilot can make a split-second intelligent decision? So that's what we are talking about. It's essentially trying to create and supplement human decision processes with more knowledge from multiple domains simultaneously. Advanced transportation. This is another area where computing technology can significantly assist. Recently, as you might have read, I don't know if you have, how many of you have read that article recently about Google piloting a self-driven vehicle? Well, I'm sure being Google, you should be able to Google it and be able to find it. But the whole concept is that, as you know, we have an aging population. And one of the things we want to do is to be able to continue to assist them to be able to get from place to place. So a novel idea is to have self-driven cars. It's almost like getting into a monorail or one of these transit systems in large cities where many of those trains run on its own. In fact, people have found they run more on time and safer. In fact, if you look at how some of the things regarding flight is concerned, even our most advanced planes, practically they can fly by itself using radar and landing technologies and being able to factor in multiple data. So very much similar to what I already talked about under decision systems. But anyway, what I'm trying to say here is how we can couple transportation technologies with computing. As you can also see, many of the cars right now, they have more computers, several hundred computers or that actually guide the actual capability of the engine and how it needs to respond already in our society. But now this is taking it to the next level in which basically the car is going to drive by itself. You have also seen several cars that have advertised, and more are on the way, that are able to self-park in a parallel parking. I don't know how many of you have to do that anymore when you have to get a driver's test. I know I had to do that, and that is one of the hardest parts of the test. But now you have cars that basically are able to self-park, which is phenomenal. The next thing I want to talk about is big data. The thing about big data is, as you can see, there are more and more people generating more and more data. In the example that I said about aircraft engines, we have several hundred instrumentation points on that engine which constantly feed the data. You can also think about in a warehouse where we are storing in supplies and products, where we have attached what we call RFIDs, which is radio frequency identification tags, which constantly emit its location and the volume of the pallet that it's in. As you can imagine, this data is constantly collected. So if it's sending a signal every 5 seconds to 10 seconds, you can see it significantly increases the volume. In fact, right now, I believe the internet, there's more things providing data onto the internet than actual human beings. So the explosion of data is phenomenal. Now, how do we make use of all this data? Because as you can see, even in the warehouse example, after a period of time, after the merchandise has been picked up and distributed, it's no longer meaningful to continue to keep that information. So there is a life expectancy, or half-life if you want to look at it that way, of data. But the important thing is that how do we make those kinds of decisions? This is, and also when you collect large amounts of data, like points of sales, and Walmart has done it for many years, they're able to look at practically in the thousands of stores globally on any particular shelf when a particular product has been picked up by the consumer and been purchased. And that automatically sends an order back to their suppliers to make sure that item gets restocked in a hurry. So if the frequency of an item being purchased off the shelf is high, they want to make sure they inform the supplier accordingly so they never run out of the merchandise. I mean, that's one of the things I think Walmart has perfected. But that is a business type of application. Similarly, you can look at big data in medical applications as well. And I think I have another one that comes up regarding medical data and informatics, and I'll talk a little bit more about that. But the whole concept about big data is how do we analyze large volumes of data quickly for the salient features we are looking for. So I'm sure you're familiar with that already. I know all of you use email, and you can imagine how much volume of data of emails that you get. And you already know not a lot of that is not significant. But the thing is that how are you able to sort through, be able to look at those few that are most significant? And so big data is about that. It's also about predictive analytics, because you can collect data, large volumes of data, using statistical pattern recognition techniques. You can identify what's the salient characteristics. And one of the things that I personally worked on is looking at speech data, and then using that speech data to identify what common words are spoken by different types of people, because their accent and attenuation and the way they speak is quite different, but they mean the same thing. I have also used the data to take a look at how I can use unique characteristics of their speech to be able to identify who the speaker is. So this is a case in which you're doing speech analysis. One set of data would tell you we need to minimize variability of what they're saying, and the same data can also be used depending upon what features you extract from it as to what the unique quality of an individual is, so that we can identify that as almost like a fingerprint in terms of who that unique person is. So you can see there's lots of things you can do with data in terms of being able to look at it. But first and foremost, you have to remember it's all about yes, we can do a lot of analysis, but if your measurement technologies are not good, you will not even be able to succeed. I mean, a lot of scientific knowledge came about as a result of people inventing the microscope, because they're able to now include a method of measurement which was not available before, and that started another significant advance in scientific breakthrough. Now, I wanted to include a topic on collaboration, because as you can see, my fundamental belief in learning and education, and also in terms of scientific breakthrough, comes when people collaborate with each other. We build on each other's ideas. We build on each other's work that was done before. So I think it's significant that we continue that. That's how essentially scientific breakthroughs are done. So how can we use information technology to improve that component, which is an essential cornerstone of human progress, which is collaboration? So the way we do that is to be able to provide both synchronous and asynchronous collaboration. Now, historically, only possibility to the best extent that was possible was synchronous collaboration, when we all meet in a certain place and we work on a problem together. That has a lot of advantages. However, can we do that when we are separated from in space and in time? And information technology makes that possible. So I can work on a problem for a while and leave it in a place where other people can have access to it and continue developing it. And this is very practical in the sense of software development. We all work towards a same set of requirements, but I'm able to work on it in the United States, and then somebody in Europe can pick it up a few hours later, and somebody in the Middle East can work on it a few hours later, and then Asia a few hours later, and before you know it, the whole day someone somewhere is always working on that problem. And one of the things we have done at NASA is to hold what we call these activities called random acts of kindness, which is an ability where people gather both physically and also in computer and in cyberspace to be able to collaborate on big challenge problems. And actually we have been able to do that to quite a degree, and we have generated quite a degree of success based on that, because people have been able to collaborate on significant NASA challenges, and we were able to use the work of the people collaborating globally. So that's more of that will be coming in the future. Let me switch topics slightly now. We're going to be talking about health informatics. As you know, more and more medical capabilities are being enhanced by information technology. People can predict as to your capabilities in terms of how you react to a medicine, significantly advanced by gene therapy. But when you look at individual genes and then take a look at how each variability of that is contributed by a human being, you're talking about volumes and volumes of data. Now, how do you again sift through this to be able to come up with what we call the new form of medicine, in which the doctors can prescribe specific medicine that's targeted to you, rather than based on large statistical type of information we had collected about a class of patients and then treating, assuming everybody reacts to the same type of drug the same way with the same benefits. So there's a huge amount of work that's going to go in there. On the business side, this is again a case in which large volumes of data about you as an individual could be collected and be stored electronically, which means it can be accessible by any one of the medical providers, so that no matter where you go, the people who are treating you would have the latest information about your health records. And that will significantly, again, improve the outcomes of situations that people might find themselves in. Now, I think it would not be fair if I didn't talk a little bit about educational support systems. One of the things we always find, I think, as you go on to college and so on and so forth, especially in large freshman classes, hundreds of people take the same course, like entrance to physics and chemistry and so on and so forth. The probability of getting individualized instruction diminishes. However, once again, you find information technology coming to the rescue. This is a case in which a professor can actually, what I call, chunk their lecture into manageable pieces in terms of wrapped around a single concept. And so the lecture could be given, and then at the same time, after that lecture is given, the professor can essentially administer a test for comprehension in real time. And based on that test, the results would be available immediately. The professor can decide whether he or she has to repeat that lecture or enhance it in such a way that there is better comprehension if majority of the people did not understand that concept. However, if he or she finds that majority of the people did understand, but let's say 10% of the class did not, how do we go about doing that? So this is a case where additional information could be targeted to that student, maybe in the forms of additional reading or additional tests or additional homework, to make sure that particular concept has been understood. Because in education, as you all know, the second concept is built on the previous one. So a thorough understanding of every one of these elementary steps is critical for progress. So that's a simple example how an educational system using information technology and real-time assessment can be used to guide the professor in real time and how that lecture needs to be provided to the students. Then let me talk about the next two things. One is virtual reality and augmented reality. Virtual reality, we have done quite a bit of experiments in which, again, can be coupled with the educational requirements. It can also be coupled with medical results in which people can see three-dimensional aspects of medical data in which essentially you're interacting in cyberspace. Second Life is one of the environments in which you can actually model scientific information. At NASA, one of the things we did was recreated some of the scientific exhibits that we had in physical space and in real life, and be able to create these things in virtual reality in which anybody on the internet could interact with that model and be able to understand the concepts of lift and drag when it comes to flying planes. So this is a mechanism by which students can learn on their own and at the same time be able to interact in an environment as if it's the real thing and still appreciate some of the more sophisticated concepts of whether it's aircraft design or propulsion. But of course, it can be applied in many other areas as well. Augmented reality is a mechanism by which you can use existing technologies to create an example of how that object looks in 3 dimensions. And I have a demo that I will show you, and then you'll be able to better appreciate that. NASA used this to essentially model the Curiosity robot that was soft landed on Mars. And you can walk around the model practically to see how it was constructed. Like I mentioned to you earlier in the presentation, I wanted to show you a practical application of augmented reality. NASA has created this so you can view very many different either satellites or robots based on this technology. And you can download this application for your use at no charge from the App Store the Apple maintains. So what I have here is a printout, and you can probably make out what this is. It just looks like a bed of stones. But it's amazing when you put your camera and then you have the app running on your iPhone, and we'll have an Android version soon. And as soon as I show the camera on this, the robot actually comes to life. And you can see that very clearly. And the nice thing about this, if it's on a piece of paper, you can actually bend it, and then you can start to see the side of the wheel and the spokes associated with it. It's fabulous. And the other thing I also wanted to mention to you is the fact that you can rotate and actually interact with the robot. Now this robot actually, what you're seeing here is a CAD 3D representation of the actual robot that's roving on Mars right now. Let me see if I can get the robotic arm to work. takes a little bit of practice to make that work, but anyway, you get the idea. So you can see it now, going back and forth. So I just wanted you to be aware of this. And this technology, of course, not only applicable in the scientific world, but it's also applicable in the consumer world. Just imagine now, companies can ship out an application, whether it's a new dress or a suit or a pair of shoes, that people can actually look at it from a three-dimensional perspective rather than just seeing pictures on a catalog. So this has great implications on how business could be conducted in the future. So please share it with your friends and enjoy. So now you can see the power of information technology. Even without having seen the real model, you can appreciate the complexity of the design, but we make that design available to practically everybody on Earth, and hopefully in the future, other planets as well. So let me, by the way, we will be providing a link so that you can download that to your favorite mobile device. And right now, we believe we have that application running on iOS devices, primarily iPhones. They will be coming out with a new version for Android phones as well. Please share it with your friends. Get them more excited about science and technology, and this provides a good tool to be able to do that. Of course, information technology makes it all possible. Now let me change a little bit and talk about information technology as a profession, because ultimately that's what you all need to do in terms of selecting what your future career is going to be. So information technology basically has, I would say, two areas of emphasis. One comes from the math component. If you're very strong in math, we found most people do quite well in software. It doesn't mean that other people cannot do that, but there is a propensity and there's a natural similarity in terms of proficiency in math and being able to do very good software design. So software consists of analysis and applications and operating systems, and we kind of label that field primarily as computer science. Now the other approach to information technology is from the engineering side, which is the electrical and electronic components, and that primarily people who do that focus on hardware, and that starts with the basic elementary building foundation of hardware, and then designing the input-output systems, and then a small layer of software which we call the executive, which rides on it, which actually interacts with the basic hardware. And some of the computers, as you know, it's called the BIOS, basic input-output system, which actually implements the software called the executive. So that's the computer engineering component. So primarily, simplistically, I should say, the field is divided into two components. It doesn't mean that you cannot cross over from one to the other. Several people find maybe after a while software is more exciting than do that. And then people who have gained some more understanding about electronics want to transition into hardware. So that's the way the profession is split up. Now in terms of application, again, I broadly categorize information technology into two components, what I call infrastructure IT and mission-related IT. Infrastructure IT is about the devices itself, the desktops, the phones, and the type of phones you have, the basic network components, back office where the servers are and operating systems are maintained and applications are done, are hosted there. And we also have what we call high-performance computing, in which we do parallelization in terms of multiple computers working on the same problem. We kind of categorize them as clusters. And storage, as you probably heard about cloud and so on and so forth, in terms of being able to remotely store your information. So all these are significant aspects of how you put a computing environment together. And at the bottom of all this, which is significant and most important, is IT security. We want to make sure the systems that we deploy are safe from unauthorized access and unauthorized modification. And we are only provide the information to those who need it. So IT security has to be thought about when you're designing the hardware, and you're also designing the software and how we make that possible. Now, mission-related IT is specifically related to the fact of how we use information technology to advance a specific area. Previously, I talked about the several components of information technology, whether it's medical or whether it's in scientific analysis and so on and so forth. So some of the things that are focused on is something called data systems, in which we collect data across multiple sources and be able to analyze it, store it, and manipulate and analyze it. And control systems are the things that I talked a little bit about, which is closely coupled to autonomous systems, in which a pilot has to make a decision based on autonomous systems. And I remember I also mentioned about the Google car, which drives itself, which is essentially another autonomous system. Then human-rated systems are the things in which we expect human beings to be part of that, whether in terms of their safety and protection. So we talked a little bit about how airplanes are being designed, which practically can fly on their own and is capable of protecting the human payload. And we try to do the same thing at NASA. We definitely tried to do that at NASA as well in terms of designing spacecraft. Analysis software, again, it goes to what I talked a little bit about, big data and how we can extract significant pieces of information and knowledge based on the underlying data. So that goes to analytical software, and decision support systems are coupled with that as well. So what kind of positions can you aspire to if you're an information technology specialist? Obviously, some of the infrastructure components are related to IT operations. And then when you're designing applications, you have to lay out the entire application and then be able to modularize it. Then all these things require a level of project management in which you're integrating multiple systems together to a unique outcome in terms of a single system. And I already talked about IT security. It's a huge field in which almost no matter what area or specialty you're in, whether you're in banking, health, education, no matter, and other types of specific discipline areas, IT security is going to be a crucial component of that. Enterprise architect is one who actually designs from strategy to business processes to specific building blocks, how we would go about supporting that entire enterprise based on information technology as being a key enabler. You can be one like me, called chief technologist, who has acquired some level of understanding on all these technologies and are able to vision as to what the next thing is down the road. So we, as an enterprise, as NASA, we're looking to see how we can harness some of those clever ideas, and clever ideas come from everyone, and be able to provide a mechanism to bring those things into the NASA environment as general purpose computing technologies. IT and policy and governance comes from, like anything else, it's more of a business-oriented component, but in order to be able to create that, you have to understand the underlying technologies. One of the things I'm actually working on now is to bring your own device to work, and what does that mean to NASA's policy in terms of use of information technology in the workplace. Then, of course, you can be a chief information officer, who oversees very many of these things that I just finished talking about it. And I was a chief information officer at one of the NASA centers before I became a chief technology officer at the agency level. So as you can see, there's a lot of choices. And again, I'm sure I didn't list all of them. This is not meant to be an exhaustive list, but just to give you a flavor. This is an old graph, but at least I wanted to tell you, one of the concerns about information technology, often you read in the newspapers about outsourcing. Have you read any of those articles? I can see that you keep up with what's happening in the world. So that's important. But there has been studies which shows no matter how many jobs are being outsourced, there's such a crying need for even more jobs. And I have more slides that talks about that. But as you can see, there was a dip in terms of the number of degrees that were granted in computer science. And those talk about bachelor's, master's, and Ph.D. But I think this is an alarming situation which is unnecessary. And these graphs talk about specific degrees to women and minorities, but as you can see, we want everyone to be in this field. That's how we get to be the best. Now, these are graphs that tells you about scientific fields, and what I wanted you to do is pay particular attention to mathematics and computer science, which is the middle set of those bar charts, which shows significant amount of job openings from 2006 to projected to 2016. And you can see computing technologies far outpaces other scientific and engineering disciplines. So this is a good field to get into, is what this graph tells you. So this is another way of looking at the same chart, but as you can see, the blue area called information technology, and then if you combine mathematics into it, you can see that really commands a significant amount of projected new openings from all the way to 2016. So if you're going to pick a profession, you want to pick one in which you see a large number of scientific openings. By the way, I talked a little bit about outsourcing. Even if you outsource based on the current trend, there aren't enough people in the world, including India and China, who can occupy all these future openings. So there's still a crying demand for people to go into information technology professions right here in this country. And bottom line is, computing is where the jobs are, and these two graphs basically speak to that in terms of new jobs and replacements, and on the left side, and then specifically only the new jobs on the right side. And you can see pretty much 60 to 70%, and especially the 70% of the new jobs are all in computing. It makes a pressing case for why you should consider information technology as a career. And again, specifically within information technology, where are the jobs? Obviously, computer programmers, computer software designers, engineers, and support specialists, and system analysts, they're the ones who outshine. Now, that doesn't mean that other jobs are not important, but you can see huge opportunity. And as I talked about earlier, mobility is going to make the software design engineers and system analysts even more in demand. So I want to so one more thing I want to say. In the future, what's happening in the computing is social media. I'm sure how many of you use Facebook or LinkedIn or Twitter? Practically everybody in the room. So you can see social media is a significant component of how people are going to interact with each other, and that brings up the component of collaboration I mentioned earlier. The other significant revolution that's happening is cloud. Cloud is a mechanism by which you can essentially do your storage remotely. The whole idea of computing, I think, in my mind, is going to be revolutionized by the fact that you're going to be able to take a computer and split its components, the computing piece, the storage piece, and applications, and be able to basically separate them into different components. So in other words, when you're picking up a computer, a laptop, or a tablet, or a mobile device, you're really picking that up from a user interface perspective, as opposed to having everything being totally self-contained. Because at some point, you want to look at something using a small device, because human being who we are, we prefer something small we can carry with us all the time. But you cannot look at a huge spreadsheet, or you cannot do three-dimensional drawings on a small mobile device like your smartphone. So you have to break up a tablet or a laptop and so on and so forth. But the whole concept is you don't want to be tied up moving all the data and applications with each of those devices. You want the data to be available from anytime, anywhere. Anytime computing is the concept that we're moving towards. So the whole field of how computing is going to happen is going to be significantly different in the future. So let me close with basically a cartoon. I don't know if you can read that. It's one of the students is saying, well, I want to make sure I prepare myself for the future because I created a virus that will go off the year that I graduate. So please don't do that, but as you can see, I don't think you have to do that based on the slides I already presented as to what the future openings are in information technology. Well, I appreciate you taking the time to listen to this presentation, and hopefully, if nothing else, I convinced you that information technology is an exciting and continues to be a blossoming field way into the future. Thank you for listening.